So I'm going to try and do a screen capture, and hopefully that'll be a good workaround. Let's see. It's David Ryman, and I've been a math teacher for 5 years. In this 5-minute video, I intend to do an algebra-based proof for why the volume of a pyramid is equal to 1/3 times the area of its base times its height. So a pyramid is any three-dimensional solid with triangular lateral faces and any polygonal base with a single vertex at the very top of the pyramid. Now I'm going to pull up a Google SketchUp document that'll show you an arbitrary pyramid. This pyramid does not have a regular base, but it does have triangular lateral faces, and we want to be able to find the volume of this pyramid just as well as any regular pyramid. What you'll notice is that viewed from any side, this pyramid looks like a triangle, at least its cross-section is triangular. We're going to leverage that fact in order to continue this proof. The way that we're going to calculate the volume of the pyramid is by using what we know about the volume of prisms, that is to say the volume of each prism is the area of its base times its height, and then we're going to add up a series of prisms and make those prisms like Chichen Itza, which is, of course, a stacked pyramid instead of a true pyramid. You'll see where we're going from here. So we'll divide the pyramid up into d divisions. In this case, d appears to be 7, but d is intended to be an arbitrary number of divisions. If the total height from the base to the vertex is h, then of course the height of each of those regularly spaced divisions is going to be h over d. The volume of the topmost pyramid is going to be the area of its base times its height. In other words, the area of the first base, or b1, times h over d. And of course, the volume of the second prism is going to be b2, the area of the second base, times its height, which is also h over d. And you get the idea, b3, b4, each one has the same height, all the way down to the lowest level, which is going to be called bd, the dth level down, times h over d. When we add up the volumes of each of these prisms, we get the total volume of the pyramid, or at least an approximation for the total volume of the pyramid. What you'll notice is that h over d is a common term with each of these expressions, so we can factor it out. And then we're left with h over d times the sum of all of those areas. But it turns out that each of those areas is dependent on the number of divisions in the following way. We'll notice that all of these triangles are all similar triangles because each base is parallel to the base of the pyramid. So what that means is that each triangle has two congruent angles. In other words, each triangle is similar to every other triangle. We can use that knowledge in order to take a look at the similarity of each of these slices. So each slice over here is going to be proportional to the area of the base. And it turns out that those slices are in a ratio that is squared. The area of the slice to the area of the base is the square of the ratio of the distance down to the total distance. In other words, if we are 1 over d divisions down the pyramid, the area of this slice is going to be 1 over d squared times the area of the base. And we're going to use that fact right now. So the area of the bottom base we're going to call b. And the area of the first base, b1, is of course proportional to b by a multiplication of the ratio 1 squared over d squared. And by manipulating this fraction, we recognize that it becomes b over d squared times the level squared, which means that b2 is b over d squared times 2, the second level, squared, which means each subsequent base is going to be b over d squared times the level squared. We can factor out this common b over d squared term, and we're left with the sum of the first d squares, which actually has a neat, concise formula given by d times d plus 1 times 2d plus 1 over 6. There's a neat proof for that, but we won't have time for it in this 5-minute video. So we'll replace that expression with this expression, and we're going to manipulate the fraction once again. We're going to recognize that we can compare d to d. That's equal to 1 over 1. d plus 1 over d becomes 1 plus 1 over d, and then 2d plus 1 all over d is the same thing as 2 plus 1 over d. And now we're going to assume that the more divisions we make, the better the approximation we get. So if we can make infinitely many divisions, now all of a sudden 1 over d gets arbitrarily close to 0. So we get bh over 6 times 1 plus 0 times 2 plus 0. In other words, bh over 6 times 1 times 2. In other words, bh over 3. As we wanted, the volume of this pyramid is 1/3 times the area of its base times its height.